Welcome to Jingyi Liao's doctoral defense. The doctoral thesis title is Ambient Backscatter Communication in Cellular System. Honored casters and esteemed opponent, members of the audience. Today's lecture is about a very small radio idea with a very large consequence. The question I want to open with is this. How do we connect billions of devices without billions of batteries? The answer this thesis proposes is simple. We let the tiny device reflect signals that are already exist in the air. The Internet of Things is no longer a vision. It's already at billions of the devices. In 2023, there were about 15.7 billion connected IoT devices worldwide. By 2029, the forecasted is nearly 40 billions. Almost all of them today are powered by batteries. At that scale, batteries become bottleneck, cost, size, replacement, and electronic waste. The goal of this thesis is a communication technique that removes all bottlenecks, battery-free, maintenance-free device powered by ambient energy. The standardization world has already begun to move in this direction. In 3GPP, the international body of the cellular standards, Ambient IoT or AIoT become a formal work item in Release 19. It is expected to appear in Release 20 and Release 21 as a part of the 6G. In parallel, IEEE 802.11 BP defines ambient power communication for future Wi-Fi. Both efforts share the same target: ultra-low complexity, battery-free devices that live inside existing wireless networks. This thesis contributes to the physical layer that makes that vision real. The physical principle behind this thesis is quite old. In 1945, a passive listening device, the Great Seal Box designed by Thurman, worked only when illuminated by an external radio wave. In 1948, Harry Stockman published the first systematic treatment of the principle, communication by means of reflected power. The idea became commercial with RFID. A reader illuminates the tag, and the tag replies by modulating its reflection. In 2013, Liu and his colleagues at University of Washington took a further step. They reflected signals that are already in the air, ambient television, and the cellular signals, instead of dedicated carrier. An ambient backscatter communication link has three roles. The first is an ambient RF source, for example, a cellular base station. This is an illuminator. The second is a backscatter device, a BD, a tiny tag that does not generate its own carrier. It only changes how much the incoming wave is reflected by switching its antenna load. The third is a receiver, somewhere else in the network. It sees the compensate of the direct path from the source and the reflected path from the tag. The key idea is this: information is written on the reflection, not a new transmission. This thesis places backscatter device inside a cellular system. Base stations and phones already broadcast signals continuously, 4G LTE and 5G NR. The BD is a secondary system that rides on that primary cellular waveform. In 3GPP standard TR38.848, this configuration is called topology T3. That is our focus, as marked on the diagram. Because the BD shares spectrum, energy, and the infrastructure with the primary system, we call this arrangement symbiotic radio. Making this work is not easy. Three problems dominate. First, the reflected signal is roughly 1,000 times weaker than the direct path, around 30 dBs weaker. This is called direct path interference, or DPI. Second, even without the tag, the wireless channel is always changing because of the fading. These natural fluctuations can make the tag's over-modulation. Third, because we operate inside the live cellular network, we are not allowed to add a dedicated frequency band or a dedicated backscatter radar. The whole thesis is essentially answering these three constraints together. The core idea of this thesis is very simple to state. Every cellular receiver already estimates the wireless channel from the pilot signal. That is what pilot exists for. The BD changes the wireless channel by switching its reflection, so the talk's information is already inside the number that a standard cellular receiver computes anyway. Therefore, we do not build a new radio. We repurpose the channel estimator that is already exists in the phone or in the base station as backscatter reader. This gives us three properties at once: no dedicated reader, no new spectrum, and a software owning change to existing hardware. The rest of this thesis applies the central idea. The first contribution addressed direct path interference. Instead of a plain on-off gain, the tag alternates its reflection at two different switching frequencies, F0 and F1. This square wave frequency shift keying, or FSK. Seen from the receiver, this modulation looks exactly like an artificial Doppler shift in the reflected path. Natural fading sits around zero Doppler. The tag now sits at a distinct frequency offset. So the backscatter component moves away from the direct path interference in the Doppler domain. What was a hard interference cancellation problem becomes a simple filter problem, and we solve it using the owning pilot-based channel estimation at the cellular network already produced. This, this is the mathematical foundation of every receiver in the rest of this thesis. The first primary system we used is the LTE downlink. Every LTE base station continuously broadcasts a known reference signal, the cell-specific reference signal, or CRS. It's present in every subframe. Every phone estimates its channel from these CRS pilots at about 4 kHz. This estimator already exists in every LTE phone by design. Our ambient backscatter receiver simply squares and sums those channel estimates across pilot subcarriers. That produce one power sample per pilot symbol, a scalar sequence that carries the talk's FSK modulation. On this sequence, we compare two classical FSK modulators, a non-coherent energy detector and a coherent matched filter detector. The key point is this: there is no hardware change to the phone, only a software update on the receiver path. We validated the receiver 3 times. First, in linked level Monte Carlo simulation, the coherent FSK detector beats the energy detector by about an order of magnitude in bit error rate, or BER, at a moderate SNR. Second, a laboratory prototype. Two FSK tone appear clearly in the spectrogram of the channel estimate power. You can see them on the right. The tag is being read through the standard LTE channel estimator. So with no dedicated backscatter hardware. Third, over the air, we walked the receiver down the second floor corridor at Aalto to a building. You can see the down figure. Mm, and measured a BR on the order of 10 uh, power of -2 in indoor environment. So the concept works in theory, in a controlled prototype, and in a real indoor environment. The second primary system is the LT uplink. Here, the phone transmits a sounding reference signal or SRS, and the base station listens. Moving the reader to the base station gives us three advantages: better ADS, more digital signal processing, and centralized software updates. Mathematically, we derive the optimal receiver under the signal model. It is a maximum a posterior test built on a modified Basel functions of the first kind. It is closed form, but numerically impractical for real implementation. We therefore derive three traceable approximations: a correlation detector, a squared root detector, and a power detector. All three matches the optimal receiver within a fraction of a decibel. The measured BER matches a theory within about 1 decibel. For both the mathematical derivation and the practical receiver design are experimentally confirmed. Because the talk simply switches its reflection, it modulates both the downlink and the uplink at the same time. So the same target message is observed twice, once at the phone from the base station's signal, and once at the base station from the phone signal. These two observations experience different fading conditions. Combining them gives a diversity gain in bit error rate. This is particularly useful indoors, where multipath is strong and the coverage is uneven. This dual direction operates aligns naturally with the time diversion duplex reciprocity at the 5G and the future 6G system already used. The fourth contribution addresses 5G new radio, where the referencing reference signals are much sparser than in LT. With sparse pilot, more OFDM symbols carry no channel estimate at all. A pilot owning backscatter receiver quickly run out of observations. The idea we propose this is: first, let the receiver demodulate the actual data symbol as it would normally, then use those decode symbols as extra known reference. The feed and feed them back into the channel estimator. The signal processing flows on the slides shows exactly this. The standard chain from IQ sample through synchronization, channel estimation, equalization, modulation, and decoding is reused, and a second branch estimates the backscatter symbol on top. In simulation on a 10 MHz NR downlink, this delivers about 12 decibel of NR gain at the target BR of 10 power of -3. We validated the same principle on commercial DEC 2020 NR hardware, the Nordic NRF90 chip. And the measured BR tracks theory closely. Beyond any single result, the methodological contribution of this thesis is that all of the formulas of evidence agree. Closed form BR derivations, link level Monte Carlo simulations, and the real-world prototype measurements, all three consistent across every study in this thesis. There are 12 publications behind the thesis are connected by the same thread: theory, simulation, and hardware. And the receiver design has also been reproduced by external partners in field trials. That give us confidence that AMBC is no longer owning a theoretical construct. It is a deployable radio paradigm. Why does this matter beyond the laboratory? The same techniques enable battery-free sensor in agriculture, in warehouses, in hospital, and in the home. They reduce electronic waste because the device no longer need batteries that must be replaced and eventually discarded. Because the technique reuse existing cellular signal, it do not need new towers, and it does not need a new spectrum. It is, in short, a physical layer foundation of a more sustainable Internet of Things and for 6G. Several open problems remain. First, how many tasks can share the same cell without collisions? Medium access control for battery-free devices is still an open question. Second, today's derivations assume that QPSK primarily traffic. Extending them to higher order modulations is the next theoretical step. Third, the same channel estimator-based receiver enables indoor positioning using the backscatter. This is a direction that Aalto and industry are already actively exploring. Uh, these are naturally continuation of the thesis. This is the list about ambient backscatter published during my last 4-year PhD study. The doctoral thesis do not contain all of those papers' content. Uh, if you are interested, this is for your reference. I now call upon you, Professor Yuri Nurmi, as the opponent designed by Aalto University School of Electronic Engineering, to present your comments on my dissertation.